But before they show you their projects, we're very excited to have Michael Paradiso from Brown University. He is the head of the Center for Vision Research at Brown. He has also co-authored one of the most popular textbooks on neuroscience in America called Neuroscience Exploring the Brain, and he teaches one of the most popular courses at Brown. So without further ado, Michael Paradiso.
I'm going to try to get out of the way for some of this. I'm going to be standing in my own. So I'm still wrapping my head around the whole brain cafe thing, and I am very interested though in the intersection between art and science and all that. And there are I think a lot of connections. I'm going to try to touch on some of those, but I don't know if I've got the balance quite right tonight for the audience. I don't know who you are. I hope I know some of you. So. If someone's kind of dragging or too much science, just shuffle me along. And if it's, if something's interesting and I'm just sort of racing through it, then by all means ask questions. It's kind of up to you what I cover, and I'll try to not be too long. So I'm going to talk about vision. I'm interested in the brain and neuroscience in general, but I've always been very interested in vision and do research on it. I think because in a way for me, it's, I just want to understand, it seems magical. I guess it's just that simple. And how the heck does that work with this thing in our heads? And I was thinking about a little bit, my little kid in kindergarten studies the senses, and they teach you have 5 senses, of course, when you're a kid. But we're very visual creatures, and I was listing all the ways that we're very visual. Usually when you say you remember something, most of the time it's what it looked like. When you say, what was your dream like last night, usually it's, what did you see in your dream? It usually isn't your other modalities as much, or imagining something. I mean, art's all kinds of sensory modalities, but visual art's a very big part of art. And just daily experience, a lot of it's visual. So it's a lot of being human, is this one sense, and what's it all about, I guess is the question. Very briefly, what it's not, it's clearly not a movie in our head. And I like this cartoon because it's got this guy with his popcorn inside the head watching this big screen with the surround sound. And so you can sort of imagine the eyeball sending signal in and the ears sound, and then there's someone watching it. And the obvious problem is there's got to be someone to watch his, and someone to watch his, and people get teenier and teenier, and then there's really nobody there. And so this idea that our eye and our visual system works like a camera, it isn't like that, and that's why it's hard. If it was like that, Sony already solved the problem, or Nikon, or whatever, right? It's nothing like that. The first stage of the eye is a little bit like a camera, but all the rest is incredibly different. And to be honest, it's probably why, if you said, gee, we want an artificial visual system in a stadium to detect bad guys, keep Al-Qaeda out of the Super Bowl or whatever by recognizing terrorist suspects, well, forget it, The idea that a machine can do what humans do visually is a fair ways off. So this is what we have. We've got this thing, it's about 3 pounds. Incredibly metabolically hungry. It uses about 20% of the oxygen that's in your blood, about 50%, I think, of the glucose. Very, very hungry thing, even when you're sleeping. About 100 billion neurons. They're going all the time, unfortunately. This is what the visual system looks like in a couple different ways. Here's a pretty cartoon. So your eye, you've got the retina on the back of your eye, and then the wires go in, the optic nerve goes in, and you've got a waist station in your thalamus. And then you come back here to cerebral cortex, right? The outside covering of your brain is the cerebral cortex. And I'm going to use this simple nomenclature that's commonly used. The visual parts of the brain are just V1, V2, V12, whatever they are. And here's a flow diagram that just makes it all crystal clear. Somehow the eye, and then somehow in all this 30 or so areas, that's who we are. That's everything about what we think of as being our visual existence is in this stuff. We have no idea how, and that's of course a big part of what we're trying to figure out. The numbers are kind of interesting, and I think they're telling for how the brain works and maybe why it's not like some machine that we invent. The number of wires that actually go out the back of your eye, there's about 1 million of them. Now, just in this first area, there are 160 million. So, you've got a whole lot of stuff in your eye and only a few wires to send all the signals to your brain. And then there's this enormous hundreds and hundreds of millions of cells that process all this. The reason is probably just an evolutionary thing, that if you had a lot more wires, it would be, it'd be like a big trunk line on a telephone system or something. It couldn't be this little skinny wire that we have in our heads, and it would take up too much space. So we've got this, but it's led to all sorts of interesting design changes in the system, it seems. Now, getting to vision itself, there are lots of different tacks we could take and try to think about vision in the brain. And one I thought we'd do for simplicity's sake is to just think of the different things that are what we consider vision as one thing. And one of them is motion, that things in the world move. That's part of seeing. There's color, there's lightness values, there's form. You could say there's depth, all kinds of things. You could say. These are all distinct aspects that you can study in vision. And it turns out they're not all processed the same way. And before talking about a few of these distinct attributes, I wanted to make the point that across all these attributes, you just actually don't see most of what's coming into your eye most of the time. And this is a big way that vision is very different from your digital camera. When you point it, even if you're not looking at the viewfinder, everything that the lens is seeing is recorded all the time. We're not like that. So if you've ever been tormented by Where's Waldo, you know what I'm talking about. Now, I'm going to show you a couple demos. Now, some people in the audience may have seen these because everyone sees YouTube, and there are even people in this audience that have been in a class of mine, so not fair. But I'm going to show you a little funny thing. And you're supposed to be quiet, but the game here is, it's a little slideshow. It's going back and forth between two pictures, and something big is changing between two pictures. Don't say it, but raise your hand when you see what's changing from picture A to picture B as it toggles back and forth. All right, these smarties in the front row. Give yourself a minute. Don't feel bad. It took me a while. All right, what's changed?
There's a round, whatever that round thing is.
It's the engine.
Yeah, that right.
It's being pulled off on half the picture. It's the engine. You want to be on this one, not on that one. Right? All right, so it's a big change, but you don't notice it. Right? I'll give you one more just for fun, because these are a kick. Here's another one. Same kind of deal. See if you can tell what's changing. The circle is supposed to distract you. Takes a while. Yeah, what's changing in this one?
It's the color in the pants.
The guy's pants are going to be from khaki. All right. So the point is that, as I was saying, is that even though the key thing is all this stuff's always coming into your eye, but you're not aware of it. So there's a big difference between just light coming in and actually perceiving or being conscious of stuff. And they're incredible demonstrations of this. It's one of the reasons you should be skeptical or worried about things like eyewitness testimony, because people are in places, they see things, but they don't actually see a lot of what's there. It's a problem. Now, briefly, what you can see if you look at brain activity is, like in fMRI machines, is that the amount of brain activation in these early visual areas shifts as you focus your attention on one thing or you move your attention around. You can see the amount of brain activity growing or shrinking and shifting around in accord with this process we do of selectively examining things. So vision is a very active thing. We choose what to concentrate on. I'm going to highlight just a couple of these visual areas having to do with distinct attributes. And the first one is this one right back there. If you poke the back of your head, if you fall back on the back of your head, you'll see stars because you'll whack this area right here. And it seems to me involved in extracting edges from very complex pictures. So let's just look at a little bit of that. This is the brief neurophysiology lecture part of the talk. So here's an experiment. You've got, this poor person's had their head sliced, but if they didn't, they're looking at this screen. There's an electrode in their brain, and there's a little bar of light being swept across the screen. And you're listening to one neuron. I'm going to play you a brief bit of this little video here, which comes from these two brilliant fellows who got a Nobel Prize some years ago. Let's see if I get the sound working. That's one cell in your brain firing as they move this bar light. You see how it likes a bar tilted that way? You tilt it another way, it doesn't like it so much. Tilt it a little bit more, it completely shuts up. So this is a cell
Is it the sound you're saying that means it likes it?
The sound is a neuron, the electrical signal from one neuron put into an amplifier and a speaker so you can hear what it sounds like.
So, but that's when it likes it, and when you don't hear the
Exactly.
sound, that's when it doesn't.
Exactly. The more noise, the more it's responding to it. That's right. So,
Sorry, I'm sick.
this is an example of a cell that seems to detect edges or respond to contours or something. In this case, most of the ones in your brain, if you want to know, respond to an area about the size of a fingernail at arm's length, something like that. That's about how much information one cell is processing back here. You have hundreds of millions of these things to sort of work out the whole world. And somehow you have to stitch that all together. That's a whole other trick. And so, at this very first stage of your cerebral cortex, what we know is that you have different cells representing different pieces of different little contours. The world's kind of broken apart and turned into a little contour world, sort of like that little form figure that I showed before. And one of the reasons I think that's interesting is because line drawings are very powerful things for humans. And artists discovered this long ago. I mean, I don't have the oldest pictures here, but there are cave paintings that are similar to this petroglyph. This is a little more modern. But going way back when, people would represent things just by drawing the boundaries of them. Not something you actually see. Normally when you look at things, there are color and luminance differences, lightness differences, but people found that the outlines worked very well. I mean, I love some of these Picasso, the dog and the camel, and there's even ridiculous things like this, but the point is remarkably little can convey a lot if it's a line drawing. And I think that's because it's tapping into the system that we've developed in this early part of our brain. That's what we do first, we extract them. So Picasso's trick is almost like pre-digesting it for you and making it make this area go. Now there are later areas down here that actually have to assemble these into something bigger than just a little increment. This is an interesting patient who has stroke. This guy, HJA. Now I should show you this first. They showed him a picture of St. Paul's Cathedral and they asked him to draw it. Now, I don't know if he's an artist actually, but that's pretty good. I couldn't do it. And now that shows that he clearly can see lines, he can draw them just fine. But then look what he says when they show him something like this picture. A mechanical tool with a turning bit.
No.
He could describe in detail all the little elements, but he has no idea what that is. Or this one, round head, it looks like a powerful body, a fat pig over there. 4 short legs, doesn't say anything to me. And then he goes, there's a curly tail, must be a pig. This is the only thing he used to decide it's a pig, that little pig over there. So he can see the contours back here, but he can't put them together over there, okay? So he's got sort of an assembly problem. Let's talk a little bit about color. Color is probably the most amazing thing because it absolutely doesn't exist in the world. At least contours sort of exist in the world. Color is just absolutely created in our brains, right? So we have this light coming from the sky or from our artificial light. It sends out all kinds of different wavelengths of light. They bounce off the apple. Why do we say it's red? Well, because it absorbs most of the wavelengths and it bounces back the red ones. And we've evolved to call that red because we have particular kinds of photoreceptors in our eyes. You learn in school when you're in elementary school about the rods and the cones in the back of your eye and all that. And these are responsible for seeing color, which is true. I mean, roughly speaking, the relative activity of these different colored cones makes you see different colors, but different animals have different cones and they see different colors. There's no absolute in the world. We just make this up and we think it's absolute. People by and large agree. If you look at this early visual area, this first one of the things, I don't know if you can quite see this, but what you should see here is sort of a yellow ocean with darker orangish brownish islands in it. This is a really interesting system because the yellow, the ocean, is this edge system that I just mentioned. And interspersed with these little islands, these dark islands, that seem to be heavily involved in just seeing color. It's like a second system that invaded a pre-existing system for form. Some animals, like nocturnal animals, don't have the islands. They only have the ocean because they don't see color. We have both. Now, I was going to do a couple little demos, so you have to play along. All right, this one, we're just going to do a couple after images. We're just going to demonstrate that the color you see is based on ratios of these things, and that's how your brain interprets it. So you got to look at the red spot. We're going to do a couple versions of this.
not blocking the view. So stare at that. You need like 20 or 30 seconds to adapt well. And what we're doing is in different quadrants that you're looking at, you're essentially fatiguing different ones of these cones, the red ones or the blue ones or the green ones or whatever. So when I go to a gray field and you keep looking at the dot, you should see sort of a complementary color. I'll go back again. And so you're knocking out one kind of cone and you're seeing the bias shift towards the other one, so it can make you see a different color even though there's no color there. Here you're truly creating the color out of nothing, right? Because there is no color. Now I got to show you another, because this is everyone's favorite, my favorite too. It's all Spanish. Actually, you want to look at that little dot there, but not in this version, which is the black and white version, but in this weird pseudo-colored one, where everything's been inverted. So you're going to adapt by looking at that blue spot, that black spot for a few seconds. And then I'm going to go to the black and white one, and we're going to do this trick of creating color from nothing. All right, so we'll do it a couple times. All right, so 3, 2, 1, keep looking at the spot. You get this vivid blue sky. Adapt again, go back to this. This vivid blue sky and this nice green grass that you create because you've changed the distribution of activity in these cones. And you could quantify. You can feel it for a while, and then you can feel the color get sucked back out again. We'll do one more time. So, as part of this thing. Now, artists have played around. The other thing is that not only you have these local effects, but neurons speak to each other, and there's these very strong interactions between them in the brain. And they're responsible for things like this, the fact that this spot is all uniform gray, but the part over by the light edge looks darker than the part over by the dark edge. And artists have known this for a long time, and they've exploited it to create all sorts of interesting things. I like this Rembrandt one, mostly because of the sense of light that you get out of it. That in a way, it's almost as if the light coming in from the window is brighter than the background of the slide, because the contrast is so cleverly manipulated. It's this, it was quite an achievement in painting to be able to get this sense of bright light where there's no light. It's just reflection. The other thing you learn about color is that it's kind of, compared to edges, it's kind of promiscuous in the sense that, like this is pretty subtle here, but this patch should look slightly yellower than this down here. Is that true?
Yeah.
I know it's kind of subtle. But if you get closer, what you see is this is just two parallel lines. It's sort of an orange mustard line next to a purple line, if the projector were a little bluer. And just that little bit at the edge makes the whole enclosed area look totally different. Why is that? The color should be right there. Color plays by different rules than lightness. Here's another example. This doesn't work terribly well, but maybe you'll get the idea that this may look like there's kind of a blue circle of cellophane over some black lines, maybe like this. Now, of course, there's no blue there except on top of the lines, but it's called color bleeding. It flows away from the lines until it bumps into another line. And you can do this with our little after thing. We did this before, where you adapt to this, and then you look. Let's do it really quickly. So look at the red spot. And then feel how strong this after image from your cones is when I go to this gray field like that. That's what you saw before. But now I'm going to do one more time. Adapt here. And while you stare, let me just explain what I'm going to do. I'm going to show you the same gray background again, but this time, instead of showing just a blank screen of gray, I'm going to show a black screen of gray that's just got a thin border where these objects are. And see if you feel like it's any stronger or weaker. Isn't it much more intense? Yeah. There's something about the interaction between the system that's doing the contours and the system that's doing the color, that the color sprays out and then latches on to where the boundaries are, and it contains it in this area in a really powerful way. And I can't say this is an inspiration, but artists have sort of played around with representations like this for a long time, like this one where you've got the dress, you've got the draping of the dress done a certain way with lines that are supposed to indicate that, but then the color's more or less just sort of splotched on, which is not uncommon in painting, where it doesn't need to have the same precision that the contours do to convey the same thing. Oh, this is, Aaron, I have no idea how long I've been talking.
keep going.
Give me a deadline.
Probably getting close to it, but.
All right, I'll skip around.
Well, we'll just talk about one. This is just an interesting case of a.
Normally when you're colorblind, it just has to do with a defect in your cones in your eye. This is an unusual case. This is someone who is colorblind because of something that happened to their brain. Why is that interesting? Well, it tells you, it seems like there's something special about one part of your brain that you need it to see color. So here's the description. Successful artist, past 65 years. I was driving, hit by a small truck, and now I'm absolutely colorblind. My vision was such that everything appeared as viewing a black and white television screen. Flesh doesn't apart. Gray, red, and green peppers were indistinguishable. Both appear black. This person had a very difficult time eating anything. Everything was disgusting because color cues for visual cues are very important for us for eating. Anyway, it suggests that because of the lesion back here that there's something very special about one part of the brain. Everything in your eye can be perfect. All the signals can go in. But if you lose that, you lose color. I have another example here, which I'm just going to skip by, but you can show that that's also true for motion, that there's a part of your brain that everything can be normal up until this part right here, and if you lose that, you'll see the world as if it's a stroboscope, that you'll just see a snapshot and then a snapshot with no continuity in between. Which do you think is more devastating, the loss of color or the loss of motion? Motion, way more. You can live watching black and white TV, right? I mean, directors made movies on purpose this way, but lack of motion is a deadly thing, which is probably why very simple creatures evolved it very early on, because it's an escape, it's a life-saving thing, being able to see continuity. The person who can't see motion describes stepping off the curb and being almost killed every time because they see the car in the distance, they step, and boom, there it is in front of them. There's nothing in between. Now, let me see. Yeah, so I was gonna play around with motion a bit, but let's see. If we've only got a few minutes, let me jump ahead a little bit. Oh, the other interesting thing about motion is that you can create it when it's not there. Not all of this one works because it depends a lot on the scale. Do you get any sense of motion?
Yeah.
It'll kind of make you nauseous after a while. But this Japanese guy is really made some of these things. But it's very easy to create motion where it doesn't exist, just like you can make color where there is no color per se, if you understand how the brain processes it. And that involves this further along area that I'm showing here. And this is this description of this woman who has this what's called akinetopsia. All right. I'm going to end with one other thing, which is faces. And I wanted to do this because it speaks to the critical role that experience plays in the way your brain works, which is something we all these things we just take for granted. Until we all get older and our knees start going, our eyes start going, or whatever, everything's perfect, it seems so easy. And then as things start to break, you realize this is a very complicated machine, and it can go wrong 1,000 different ways. Now, the flip side of that is the way it gets to be that way is through experience with the world. So faces are very important. It's one of the first things that babies latch on to. We see faces everywhere. There's even a name for it, pareidolia. I like this one in South America. This what looks like this Indian sheep's face. Clouds, mountains. You can make them out of very little. If you've ever seen, artists do this, they can do like one line and you see a face. You want to see faces. And so it's a very important behavioral thing. And the thing to recognize is that when you see these faces, it's not because you're cognitively trying to work it out, right? It's automatic. And that's true with most of these things in the visual system, that what you think is very sophisticated, it is sophisticated, but it's in the wires. It's not something you ponder and you figure out, because you'd be dead by then if you were an animal. It has to be automatic and hardwired for survival. You have to look and instantly, danger, run, lion, whatever. You can't think big furry animal, those teeth seem remarkably big, it's coming at me pretty fast, but then you're dead. All right, so I wanted to finish with Albert Einstein. So I'm going to show you this hollow face illusion thing, which I have been told is used in the Haunted Mansion at Disney World. I don't know that for a fact, but that's what I'm told. So let me just show you Albert, because this makes another case about experience. Oh my God, it's really good. Very, very strong. All right, so I'm just going to set up a little clamp like in my Albert Einstein mask and just to make this point that so many things are hardwired in your brain that
even if you want to, you can't override them. That's the point of this exercise. So first, what have I got? So it's a hollow. It's a mask of Albert Einstein, obviously, where it's punched in this way, sticks out that way. So, all right. Now I'm going to light this from behind, and let's see if I can get this right. So you see him sticking out at you, right?
Yeah.
Okay. So that's Albert sticking out at you. Now you gotta remind yourself of the rules of physics, because you don't have to think about him normally. So I'm going to rotate him this way, and you're going to see him rotate towards me, right?
Yeah.
Okay, and he's sticking out at you. He's definitely sticking out at you. Okay, now the interesting part is what happens when it goes past sticking out at you and turns sideways, and it's going to be different for people in different parts of the room. But now, for those of people over there, and they now see him in profile, you see him head on, and you got to carefully decide which direction is he turning as I continue to rotate it this way. So he's rotating towards you guys. Now you guys get him in profile. And then most people get him. Now the question is he sticking out or is he sticking in? He should be sticking out if you're a normal brain. And so when I do something like I'm going to woggle him back and forth. So if I go like this, he should go like that. And when you go like this, it goes like this. So it has this interesting effect, which I guess is the Disney World thing. You've seen it there?
Yes.
Where you walk past it, and if you could get up and move, he would follow you with his eyes. Now, in order to do that, you have to understand that it's physically impossible, right? Because in order for him to morph like that, the plastic has got to be folding and bending as you move by, but you don't care. I'll give you one other example.
Can you take it a little further?
Oh, sorry, yeah. Okay. More this way? So the key thing here is I want to show you, remind you. Now you know this, you know all this, but let me remind you that it's sticking in, okay? There's no question that it's sticking in, right? So tell yourself that you're a smart person, you know it's sticking in, right? But then as soon as I take my hand away, boink, but you know it's sticking in. Why would it stick out? Well, because we know what faces are. Faces stick out. They don't stick in. It doesn't make any sense. And so your visual system is much more willing to tolerate the fact that this plastic is like molten and it's blending and tilting and contorting as I wiggle it. You'd rather tolerate that, which makes no physical sense at all, than admitting what's correct, which is it's not a face sticking out, it's a face sticking in, but you don't care. It doesn't make sense, right? And there are a lot of examples of this, the visual system and in the brain in general, that your experience overrides any common sense, but that's the way we're wired, and that's what you live with, essentially. I guess the end of this story would be, artists figured a lot of this stuff out a long, long time ago, and scientists are trying to figure out how it works, so when something breaks, how can you fix it? And at this stage, of those 30 or so areas, we have an inkling of what a few of them do, and there's this huge mystery. How does it all get stitched together to give you this consciousness that we all experience? It's a very big problem that I don't think will be solved tomorrow. Well, maybe future people from Neuro 1 will solve it. So I'll stop there. If anybody has questions,
Yeah, so what we'd like to do now is just take a few minutes to allow Michael to answer any questions that people might have before we move on to the next portion.
I have a question. I have a nephew who's autistic, and one of the things that they talk about is, like, one of the issues for him is that he actually sees everything in the way that you were saying we don't.
Right.
Do you agree with that? Is that
I've seen evidence for that. I've never done those studies, but I've seen evidence for that. There are certain classes of people that just have different brains, and they actually are immune to illusions, which is very interesting. And it probably has to do with something. Either the circuit is set up differently, or they experience. There's very interesting stuff about autism that, in some ways, autistic brains develop faster than normal brains, and unfortunately, they start too early and stop too early. And so they don't end up at the same endpoint that normal paced learning leads to. People think in autistic brains there are timing differences between these different systems. They're not synchronized quite right, and it leads to a certain amount of confusion about how you should stitch this all together. So I know I'm sort of hand-waving, but yeah, I read these things. Yeah.
So how, if someone is blind, are there other senses that are amplified? As I've heard that that's true. I mean,
Yeah.
where, and do they have a vision of a different kind?
Yeah.
Do
So, right. You sort of like to think that everyone who lost one sense, for God's sakes, we owe it to them that they'd have. God owes it to them. They should have better senses otherwise, right? It's only fair. It's not always true. It's probably generally not true. But that said, there are definitely documented cases of people that kind of have super modalities of other senses after losing one. And in these people nowadays, we can study their brains because we have techniques that didn't exist 20 years ago. And the brain activity of these people is very interesting. And so if you have someone that was blind from an early age, we had a fellow visit Brown. His name's Mike May. He's a subject of a New York Times bestseller, actually. It is very interesting. Guy lost his vision when he was 3 years old because he was mixing some chemicals out in his parents lived up in the mountains of California. Blew up in his face when he was 3. He was blinded from then on. Then when he was in his 50s, some, I don't know, 10 years ago, he was at the eye doctor with his wife. She was examined. The doctor said, what's with you, essentially. He looked at his eyes. I might be able to do something for you. This started this whole thing about should he see, was it right to see? He was a very successful guy, blind, so that he could see. They made him see a little bit. I'll describe that in a second. You image his brain, what do you see? Well, the visual parts of his brain that I'm showing you don't respond to light very much. They mostly respond now to sound and to touch, especially sound. And this is very common in the people that have lost one modality early. If you lose it as an adult, you're not going to get so much change. If you lose it as a young child, you can get a lot of molding in cerebral cortex where one part that becomes quiet gets taken over by other senses. And so then you can get these sort of super sensory modalities out of it. And that's the way Mike is. He's unbelievable. You've probably seen this with certain blind people that can echolocate by making sounds, or I don't know if you've ever tried Braille. I don't know how they do it. It's incredibly difficult, but people who are experienced with Braille can just completely split. I had a blind woman in the introductory nerd class a couple years ago that I teach. She takes exams with her laptop, and you can imagine in a class that involves anatomy, I had to describe, I'd say, it would be very difficult. I'd say, all right, you start off and you're on the top of the head, you go down like 3 centimeters, and then you go lateral 1 centimeter, then rostral 1 millimeter. Where are you? I couldn't do that. I need to see a picture, right? She could do it actually. But the remarkable thing was, I'm listening, she takes the exam, answering it with a special system on her laptop, and she pulls the headphones out by mistake, and I'm listening to the way she does it. It's like an auctioneer. It's like, it's incredibly fast. I couldn't understand it. She said, you get used to it, when you rely on your hearing all the time, and she could process it at this incredible speed. And a long way of saying, yeah, I think there's something to that.
Sort of in the other direction, I learned from a movie about deaf people that one of them said all deaf people can see Where's Waldo. It's not a problem for them.
Really?
And I'm wondering.
I'd be surprised by that, but
I wondered how general that is. If they're using.
I've never heard that before. That'd be interesting.
It'd be interesting if they're using.
Because
some of that part of the
I
brain.
think this whole Where's Waldo thing, you can see just from the numbers I gave you what the problem is. You've got this 1 million wires going in, and then because you have like 500 million neurons analyzing it in X, Y, and Z different ways, you just can't, your attentional system just can't focus on all those at the same time. And so it's selective. And I don't know how not having hearing or something else would change that just numerical problem of all this volume of trying to monitor it simultaneously. Maybe. If it's true, I would love to study it. It's fascinating. Yes.
Okay, I had a question of, actually last night I was here relatively late. I've been awake for a long time, like 17 hours. And I was feeling extremely fatigued. And I was trying to calibrate something that was very exact. And my spatial relationships are usually pretty good. I can usually say like 1.5 inches is like right here and like follow things across. But I was trying to bring wires to a certain depth level, to a certain point. And I actually kept forgetting mentally, I couldn't take the thing to where it needed to go. I would put it somewhere else and then sit back and think, did that go there? And when I'm wide awake, I can just be like, there it is. So I was wondering, like, over time, is sleep deprivation, like, does it actually make your vision kind of go haywire in that way?
Yeah. It's an interesting question. If you do it long enough, you'll start hallucinating. Why that is, I can't tell you, but it seems like. I mean, that's the thing is that. I think the mind and the brain are the same thing. Okay, I think the mind is an amazing thing, but somehow it's derived from this neural activity, and that's why when you hit your head, you can see. Well, why would hitting your head make you see? Well, it's just that's what those cells do. Now, in this case, what is seeing? I mean, it's some pattern of activity in certain parts of your brain. Now, evidently, when you're really sleep deprived, you start getting activity in these things, and then start interpreting it as projected things out in the real world, even though there's nothing there. And so there are all kinds of reports that are sleep deprived, and people are seeing all kinds of crazy stuff. What is that like? Well, dreams, right? That's what dreaming is. When you dream, you have all these same areas lighting up. The only difference is there's nothing in here and there's nothing in the middle. You're essentially cut off from most input from the outside world, and then you just start having this random activity, and it's sort of like seeing, I think it's like seeing faces in the clouds, that we're so good at interpreting things that we start building storylines and assigning people's appearance to all these weird patterns, and then we make them up.
Do you know if there's like a specific part of the brain that causes like stuttering or like speech impediments?
Oh, yeah, I don't know much about that, no.
Just wondering.
No. But, there are these intriguing things like people who stutter can sing without stuttering, these sorts of things, suggesting that this, of course we know what parts of the brain move the lips and the tongue that are involved, but obviously it's not that, right? Because you could sing just fine, use those same structures. It's something else that's controlling that specifically for language. And so you can kind of zero in on it that way. I could infer, but I don't know much about it.
As far as vision goes, I know you talked about how it's much different when you're younger in life and you have an impairment, that it could change or vary. But what if somebody's born with a hereditary condition that impairs their vision later in life? How does the deterioration process differ from when it's later in life versus when you're younger?
Well, I mean, I'm not sure exactly what you're thinking of. If someone's born and they develop normally, they'll see normally that time. It sounds like you're talking about something that's sort of a time bomb situation where it's ticking, and then
it's an hereditary
something
condition.
Eventually goes along, like retinitis pigmentosa or something, or macular degeneration or something.
Mm-hmm.
I mean, up until that point, these people see normally.
Of course.
One of the insidious things about these sensory disorders often is, though, that you're quite tolerant of having the deficit, so by the time you notice it, if you don't go to the doctor, it's actually fairly far progressed.
Exactly, that's what happened to my father, so that's what I'm asking.
Yeah, and that's a real problem with a lot of our. I was telling Aaron, about when we were talking the other day about some of these things that I just find amazing that don't bother us, and one of them, just a dumb example, I guess it's dumb, to me it's amazing, is going outside at night.
Mm-hmm.
I would think this would be a startling thing. You're outside during the day, you're inside under artificial light, the world is colorful, you can see all the details, and then you go outside at night, well, there's no color. Why isn't that? I would think that would just be shocking to us, but I guess we're so, I don't ever even heard of, even my little kids, I would think, you'd think at some age they go, what the hell happened? Where'd all the color? I've never heard anyone say that. I guess we just get used to it, but we're very tolerant of that. There are all sorts of, that silliness aside, there are all sorts of funny ways that we're very non-observant.
Mm-hmm.
Anyway, so these things can sneak up on you, right?
Yeah.